Good morning, everybody. So today we're going to focus on taking derivatives, except we're going to attempt to figure these out a more efficient way. So we're going to talk about the rules for differentiation here. And so let's talk a bit about the patterns that we've seen so far. So there's some rules associated with finding these derivatives. And so what we've seen so far from doing the long, drawn out, the first principles way is that if you've got y equals a constant, you've got a completely flat line here. It could be 1, 2, 3, 4, any of those. The slope of this line is always going to be 0. So the gradient of this, of any horizontal line, is going to be 0. So for a straight line, and you'll typically see this as y equals mx plus c or y equals mx plus b. This is slope-intercept form. The gradient of something in slope-intercept form is just the slope there, the value of m. So the gradient for this is a constant number, and it's just whatever your slope of this line is. And so then another function that we've looked at together more generally is y equals x squared. And if you're watching this, you should have reached that point in the problem set where you realized that the derivative here, the f prime of x, is really just 2 times whatever the x value is at that point. So like if you do the x value, if this was an x value of 2, if this was the coordinate 2, 4, at the instantaneous slope here is actually 4 as well, because it's 2 times 4. You just multiply the x value by 2. So then a general rule that you can take from this, we can generalize these results to get what's called the power rule for derivatives. So what the power rule for derivatives says is that if you take f prime of x of n, if you take the derivative of x of n, the way that you calculate that, you bring the power down and multiply by it, and then you subtract 1 from the power. So more practically, like if we've got these different functions here, like if we've got x cubed, with the derivative of x cubed, we're going to bring this down. We're going to call it 3, and then we're going to subtract. So 3 times x squared, the power decreases by 1. So like for x to the 4th, we would say that's 4x decrease the power by 1. The power comes down, it multiplies. X to the 5th, we get 5x to the 4th. X to the 6th, we get 6x to the 5th. X to the 7th, we get 7x to the 6th. So on, so forth. So a quick way to find the derivative of anything with an exponent is you bring the exponent down as multiplication and you subtract by 1. And this is just an application of all of the first principles that we've looked at. It's a pattern that if you calculate it by hand, it occurs. Somebody a lot smarter than me figured that out and discovered this pattern so we can use it so we don't have to do the long way every single time. So a couple of other derivative rules that we're going to use today is that anytime you differentiate a constant, we talked about this a little bit earlier, if f of x is just some number here, the derivative f prime of x is going to be 0. The rate of change of a constant is 0. It doesn't change. So then another thing is that if you've got a constant times some function here, to get the derivative, the constant's going to stay the same, and you're going to take the derivative of this. So like, for example, if we did the derivative of 3x squared, I'm going to bring the power down and multiply it. So that would be 6, and then we're going to do x to the 2 minus 1, x to the first. We don't need to write this first here if we don't need to. So the derivative here is f prime of x equals 6. Another derivative rule that we can use here is the rule that if you've got a function, if you got something plus something, and you take the derivative of that, you just get the u prime of x, the derivative of u plus the derivative of v. And so we're going to be using these properties to take these derivatives, except now we're not going to use the long, drawn out method to do so. So the first one that we're going to do, and Mr. Price just realized that that should be a squared. So I've realized I copied that problem down wrong. So again, we are in the orange book here, and we're going to be looking at example 8. So the first thing that we're going to do is we're going to find the derivative of y equals 5x cubed plus 6x squared minus 3x plus 2. So you could see this written a couple of ways. So dy dx means we're taking the derivative of y, taking the derivative of y with respect to x. So let's see, 5x cubed, if I bring that 3 down and multiply it, that's going to be 15x squared. If I bring this 2 down, that's going to be plus 12x. The power here on the x is a 1. If I bring that out and multiply it, that's just going to be a minus 3. And I'm not going to write x to the 0 power because anything to the 0 power is 1. I'm not going to write 3 times 1. And then this constant, the derivative of a constant, is 0. And so effectively what we have here, now this function is our derivative function. This is our derivative. And again, to emphasize what that tells us the instantaneous slope at any x value. And this is tremendously quicker than doing the first principles. But you're probably like, Mr. Price, why didn't you just show us this in the first place? You need to walk before you can run. So let's continue working with this, finding some derivatives the short way, per se. So now we're going to look at these two examples. So we're actually going to focus on, we'll focus on A first. So to calculate these derivatives, when we are writing these, we need to make sure everything is in the numerator. We need to move everything to the numerator. So again, this is a little bit of an Algebra 2 reminder. If you've got a exponent in the denominator or the numerator, and you want to make it, if you want to move its spot, you have to change the sign on the exponent. So like 4x to the negative 1 is the same thing as 4 over x. So before we take this derivative right here, I'm going to rewrite this as minus 4 times x to the negative 1 plus 3 times x to the negative third. And now when we're calculating this derivative here, we're going to use the power rule. This has an exponent of 1. So if I multiply that by 1, I'm going to get 7. That x is just going to be to the 0 power. I'm not going to bother writing it here. X to the negative 1, if I multiply negative 4 times negative 1, that's going to give me plus x. Now, negative 1 minus 1 is going to give me negative 2. And then the same thing here. Positive 3 times negative 3 is negative 9. If I subtract 1 from the power, it's going to be minus 4. And so lastly, when we're writing this derivative, if we want to substitute into it, so this is what dy dx is. We want to make sure that our final answer is positive exponents. So what I'm going to do is I'm going to bring those exponents back to our denominator to make them positive, minus 9 over x to the fourth. And this is what f prime of x is. Now you'll notice here I used dy dx here, I used f prime of x here. I want to emphasize that those are the exact same things to you all. So you're going to see me using some different notation to communicate that. So let's look at another one of these and talk about what it means. Like what are we calculating? So here we want to do the derivative of x squared plus 4x minus 5 divided by x. So to calculate this derivative, the instantaneous rate of change function, what we need to do is we've got to have this this whole thing's kind of together. We want to break this up into individual terms. So what I'm going to do is I'm going to rewrite this as everything here being divided by this x instead of it all being lumped together. We're going to break this fraction up. It's a little algebra trick here, and we're going to simplify. So that x squared over x is just x. 4x divided by x is going to be plus 4. And I'm going to rewrite this last one here as x to the negative 1. And then we need to take the derivative using that power rule. So take the derivative. So the exponent here is a 1. If I multiply this by a 1, I'm just going to get a 1. The x is going to go away. I subtract the power by 1. The derivative of this constant, derivative is 0. So we've got 1. And then the last one here, negative 5 times negative 1 is plus 5 times x to the negative second power. This is what dy dx is. The derivative of y with respect to x. And then if I want to rewrite this to where I can easily simplify, easily solve, I'm just going to bring that x squared back to the denominator. This is what our derivative function is. So we can use this derivative function to do a couple of different things. Mainly, we can use it to tell us the slope at any x value. So what we're going to do is we're going to use that. So the function that we're going to be looking at here, we got y equals x squared minus 4 divided by x. So what we want to do is we're going to find the derivative first, and then we're going to use that derivative to find the gradient of the tangent when x equals 2. So let's see. We got y equals x squared. I'm going to go ahead and rewrite that as minus 4 times x to the negative 1 power. X squared minus 4 times x to the negative 1 power. So if I use the power rule, f prime of x equals, we're going to bring this 2 down, subtract the exponent, that's 2x. Same thing here, multiply this, plus 4, and that's going to be x to the negative 2. Or if we want to write that, because we're going to have to simplify this, dy dx equals 2x plus 4 divided by x squared. That right there. This is our derivative function. So now, if we want to find the slope of the tangent at x equals 2, all that we've got to do is substitute in to our function now. So we're going to say, well, the derivative, 2 times 2, plus 4 over 2 squared. So that's going to be what? 4 plus 4 over 4, which will give us 5. So the gradient, the instantaneous slope, the rate of change, all of these things tell us the same thing, that the slope of the function at the x value of 2 is 5. Want to really emphasize that to you all. All we're doing is we're calculating slope at a certain point using a shortcut here. So then let's look at another one here. Just a shorter example of the power rule. So we've got y equals 3x squared minus 4x. They want us to find dy over dx, the root of y with respect to x, and interpret its meaning. So if we've got y equals 3x squared minus 4x, then y prime, also you could see it that way for the derivative. Let's see, 3 times 2, that's going to give me 6x minus 4. And so this function right here, if we want to interpret what this meaning is, this function tells us the instantaneous rate of change or slope Those are the same thing for any x value. That is what the power rule lets us do. We don't have to do all of that limit stuff now, which is pretty cool. Makes it a lot more efficient for us. So we're going to look at 2 more problems, and we're going to call it a day for today. 2 more problems, and we're going to call it a day for today. So we're looking at example 12. And so what we want to do is say, okay, at what point on the curve y equals 2x squared plus 5x minus 3, that's going to be a parabola looking thing. That graph's probably not accurate. That's okay. But we want to answer the question, at what point does the tangent have a gradient 13? So we want to know, when is the derivative going to be equal to 13? So the first thing that we need to do is we need to find the derivative function. So we're going to use the power rule to do so. So we're going to, let's see, multiply that. That's going to be 4x to the first power, and we'll say this is f prime of x. X to the 1 times 5 is plus 5. And then the derivative of a constant number is 0. So our derivative function right here is 4x plus 5. And so what we want to know is, when is 4x plus 5, the derivative function, equal to 13? So all we're going to do is replace the gradient here. 13 equals 4x plus 5, and we're going to solve for it. So this will probably be the easiest equation that we've solved in some amount of time. Let's see, 8 equals 4 times x. So that means that x is going to equal 2. It means x will have a value of 2 there. And so you can use this this derivative function to find the instantaneous rate of change at any point. That's the brilliance of this power rule and of the derivative function. So then the last example that we're going to look at for today, we're given the tangent to f of x equals 2x squared minus ax plus b at the point 2, 7, so this is an x and this is a y coordinate, has a gradient of 3. So we want to find out, what are the values of a and b for this quadratic, for this parabola. So we're given f of x equals 2x squared minus ax plus b. So we're going to be dealing with the gradients. So let's go ahead and find f prime of x real quick. So f prime of x equals, let's see, we multiply that. That's going to be 4x minus a. Let's see. And then b is going to go away. So we've got these 2 functions right here. We've got these 2 functions. So what we can do is we can substitute in what we know. So we know when the x value for the derivative is 2, that the gradient is 3. So we can substitute that in. 3 equals 4 times 2 minus a. And then we can also substitute in this coordinate into here. We can say 7 equals 2 times 2 squared minus a times 2 plus b. And if I clean this equation up, 7 equals 8 minus 2a plus b. So here we're stuck with 2 variables in that equation. And over here in this equation, we're given 8 minus a equals 3. So if we go and we solve for this, minus 8, and this is our derivative. This is our original. I guess I should have labeled that, sorry. So we've got negative 5 equals negative a, which just means that a is going to have a value of 5. So now, knowing that a is 5, we can go back to this equation that we substituted this xy coordinate into, and solve for it. So we can say 7 equals 8 minus 2 times 5 plus b. Let's see, 8 minus 10, that's going to be negative 2 plus b equals 7. So that means that b will equal 9. So the values of a were 5 and the values of b were 9. So I know when you first see this power rule, it takes a little bit of time to develop some intuition on how to calculate these derivatives. When you are working these problems in your homework, I would highly recommend checking your answers, as you go. Check your answers as you go and see, okay, am I doing this right? Is there something that I need to look at? Because when you're first calculating these using these shortcut rules, it's real easy to make a little mistake the entire way. So I would just make sure you're being careful with that. So if you all need anything, please let me know, and I can definitely schedule a time to meet with you about this. And if you all need anything else, please let me know. You all have a good rest of your day, and I will see you on Thursday.